We'll now talk about the concept of immunization. It is, in general, the idea of it is to create a situation where changes in interest rates don't affect the value of your portfolio, where portfolio could be asset liability portfolio or just asset portfolio, but from the point of view of an insurance company, the most important situation is when you have assets and liabilities and you worry that as a result of changes in interest rates, their values will change in such a way that you will lose money in the process. And of course, the value of an insurance firm is its assets minus liabilities, called the surplus or capital. And that surplus or capital is important to the owners of the company, but it's also important to regulators who treat it as, in a sense, a backup for the reserves. The reserves are the liabilities. That's the money that is there to pay the claims and benefits to customers. But if that's not enough, then the company's surplus will be used for that. And regulators want to make sure that there's enough in both reserves and surplus to fulfill all the obligations to the customers. Now, there are various methods of accounting for assets and liabilities, and you'll study that later. But the general idea here is that we study both assets and liabilities as functions of interest rate, and then surplus is the difference of the two, and it's also a function of interest rate. So surplus is assets minus liabilities, and every piece of that equation is treated as a function of interest rate, I. In 1952, an actuary named Reddington proposed that the idea that assets and liabilities of an insurance firm should be treated in management of the firm in an integrated fashion, and the surplus, the difference of the two, should be studied, its value, how its value changes as a result of changes in market conditions, and the most important thing is changes in interest rates. So what would we want to achieve in that management? Well, one objective could be to prevent the surplus value from changing when interest rate changes, so that the change in the value of the surplus is close to zero when the interest rate changes slightly, so that basically delta S is approximately zero and delta I is approximately zero. But that implies that the derivative of S with respect to I is basically zero, and that implies in turn that because surplus is assets minus liabilities, so that derivative of a surplus is derivative of assets minus derivative of liabilities, that the derivative of assets minus derivative of liabilities should be zero on both derivatives with respect to the interest rate. And that, in terms of what we just learned, means that the monetary or dollar duration of assets should be equal to the monetary or dollar duration of liabilities. If additionally we actually create a situation where the second derivative of the surplus with respect to the interest rate is positive, which implies that the second derivative of assets with respect to the interest rate has to be greater than the second derivative of liabilities with respect to the interest rate, then what happens is that the graph of the surplus as a function of the interest rate is convex, and that means that if there's a change in interest rate, then whichever way it goes, the new surplus will be actually positive, because where we are now, where the derivative is zero, is going to be a local minimum. And if we go to the left or to the right with the interest rate, because of convexity, we will have a higher value of the surplus. So that's, in a sense, an idealized condition that Reddington envisioned. And this is a form of protection against interest rate risk. So this form of immunization can be summarized as this idea that to protect the absolute surplus level, the amount of a surplus, we set the derivative of the assets with respect to the interest rate equal to the derivative of the liabilities with respect to the interest rate. And that means monetary duration of assets equal to monetary duration of liabilities. And then the second derivative of assets with respect to the interest rate is greater than the second derivative of liabilities with respect to the interest rate. And that means that we choose assets with more monetary convexity than the monetary convexity of liabilities. And again, I say monetary when most of investment people that you meet to talk about this will say dollar convexity, dollar duration, and so on. But it's the same idea. But things are not really that simple in practical management of insurance firms, because the regulators are not just concerned with the question of whether you have surplus, but also they want to make sure that the ratio of your surplus to assets or the ratio of surplus to liabilities is appropriately big. You're actually supposed to have this capital ratio being above a certain level prescribed by regulation. And in this case, the firm would be interested in setting something that would address the change in the ratio of assets to liabilities with respect to the interest rate. But if you take the natural logarithm of a ratio, then that's a natural logarithm of a difference. I'm sorry, I didn't say it right. Natural logarithm of a ratio, so ln of a over L, it's the same as ln of a minus ln of L. So natural logarithm of a ratio is the difference of natural logarithms. And if you want that quantity to be close to 0 or 0, then you want the derivative of the natural logarithm of assets to be the same as the derivative of natural logarithm of liabilities. In other words, you want duration of assets equal to the duration of liabilities. And then, in order to achieve the situation that whatever happens to interest rates, you end up with more after the change in interest rates, then you want the second derivative of natural logarithm of the assets with respect to the interest rate to be greater than the second derivative of natural logarithm of liabilities. And that basically means that you want to choose assets with more m squared or dispersion than that of liabilities. But when durations are equal, greater m squared is equivalent to greater convexity. So that one can also set this condition as convexity of assets exceeding convexity of liabilities. And in fact, Reddington immunization refers to a creation of a portfolio of assets such that assets value equals to the value of liabilities, because remember, liabilities are given through the products that you sold if you're an insurance company. And then through your management, you have to decide what kind of assets you're going to buy. So you buy assets that are equal to the value of liabilities, and duration of the asset portfolio equals to the duration of the liabilities portfolio, and convexity of the asset portfolio exceeds the convexity of the liabilities portfolio. And we also say that an asset liability portfolio is fully immunized if for any interest rate change, the value of the assets is greater than or equal to the value of the liabilities. Well, all this may sound nice with all the relatively simple but convincing mathematics behind it, but the concept of immunization has many critics, and there are problems commonly quoted, listed about the immunization process. First, we assume only one interest rate, and then we assume that that interest rate moves up and down the same way for every maturity. And of course, that's not really how things look in the real world. We'll talk about the yield curve very soon. Immunization assumes only instantaneous, infinitely small change in all interest rates for all maturities. That set of all interest rates for all maturities is called the yield curve. And it's of course not exactly how things work in real life. And if you're a financial intermediary, which means a bank, insurance company, investment company, you watch interest rates all the time, and you're very worried about changes in them. And if you do that, you see that that's not really a typical change in interest rates. And then immunization requires continuous costly rebalancing, because whenever you diverge from your condition of duration of assets equal to duration of liabilities, you have to buy new assets. So you have to sell the ones that you have, buy new ones to fix things, and so on. and to fix convexity. And of course, that happens actually when interest rates change, but it also happens because of passage of time. Because passage of time means that some of your assets, which are typically bonds, will be paid off and you have to buy new ones. And all of this involves transaction costs that can be quite substantial. There's actually a way to fix this. There is another method of asset liability management that avoids all the problems with immunization, but it's much more costly. This method is called dedication or cash flow matching, and it simply says that you should buy assets that make payments, exactly the same payments that are needed to pay your liabilities. So if you owe your customer a payment of $5,000 in, say, 2 years, exactly $5,000 in 2 years, then simply buy a 2-year government bond, federal government, to make it sure that it's definitely paid. That will be paid in the amount needed at exactly the time needed. Now, that's not always possible, but if liabilities are relatively simple, it is. If liabilities cash flows are random, that's not really possible at all. And of course, if liabilities and assets in this approach produce exactly the same cash flows throughout the existence of liabilities, then they must have exactly the same present value. Dedication is actually similar to a more general strategy called hedging. Hedging refers to a situation when an investor faces a risk of some type, risk of a loss from either some asset portfolio the investor holds, or from having liabilities to the customers, and then the value of liabilities can increase, so that's costly. And in order to manage the risk, the investor buys or sells a financial instrument. Financial instrument means anything that pays money in the future, so stocks, bonds, some derivative security, whatever you can find. And that financial instrument is called a hedge that moves in the opposite direction of that of the current exposure. In other words, if you're at the risk of losing money, buy something that will make you money at the same time when the loss occurs. So, for example, an annuity company may offer a minimum interest rate guarantee of 4% to its customers. And with the current very low interest rates, this looks like a very risky idea, but it once didn't. So in order to manage that exposure, the company can buy a long-term government bond for the same amount as the annuity, which pays a 4% coupon. So they will get 4% interest rate from the government bond. That would help manage the risk, but it would not be ideal, as the bond would eventually mature, and bonds have shorter maturities than lengths of deferred annuity contracts. So it's a relatively imperfect hedge. A perfect hedge would be an instrument that pays the insurance company the difference between 4% and the rate earned by the company's asset portfolio if the asset portfolio earns less than 4%, because they promise the customers that 4%. That kind of instrument is actually called a floor, although the floor described here would be almost impossible to buy unless somebody is really willing to pay you something like this for a price, of course. Now, dedication is also an example of a certain ideal strategy, which, although non-existent in reality, is often vigorously pursued in hope of getting free money. As economists would say, often free lunch. The strategy is called arbitrage. Arbitrage is a situation when an investor does not spend any of his or her money, but manages to create a portfolio that provides income with positive probability and never loses money. So it's like free money or free lunch. One example of such a situation would be if the same financial instrument sold for 2 different prices at the same time. So if you could buy a U.S. government bond in Philadelphia for a different price than in New York, then you should buy the cheap one and sell the one that is expensive immediately and then pocket the difference. That's a true arbitrage. Now, why do we talk about all this? Because there are real-world issues that come up in interest rate risk management, and also if you manage to find a portfolio that will pay you a specific fixed interest rate while you pay your customers less, you basically make free money. Look at this exercise here. You are given the following information concerning an immunization strategy considered by an insurance company. An initial portfolio value that the company has is $10 million. The minimum return required on this portfolio is 4%. Now, if the company earns this return, the current assets can be used to pay off the liability in full at the end of the investment horizon, which is 10 years. But it's also possible to find a portfolio that will pay exactly 8%. It's possible to find a portfolio that over the investment horizon will earn 8%. Assuming that the immunized portfolio exists and can work perfectly, if implemented, calculate the difference between the initial portfolio value and the required assets for immunization at inception. Now, the company has $10 million. It's supposed to pay 4% on that $10 million over 10 years. And it's not every year, it's all combined after 10 years. But they can earn 8. And the point is that will earn them more or less free money. Okay, so if they're supposed to earn 4% over 10 years, then 10 million accumulated 4% over 10 years is worth 10 million times 1.04 to the 10th, or approximately 2,442.80. Okay, but the insurance company can earn 8% if it implements the immunization strategy perfectly. How much money do you need today to, if it earns 8%, to accumulate that 14,802,000? Well, present value of 14,802,442.80 at 8% over 10 years, and that ends up being just slightly under 7 million. And the difference between 10 million that they have and slightly under 6.9 million that they need, which is 3,143,604.86, is basically a profit that this company could pocket, and that's the difference that we were looking for.